In this lecture, we'll be looking essentially at mission analysis for a number of vehicles, and each of these vehicles will actually use the same engine. It's the same fourth generation engine which enables us to get high specific thrust and also useful acceleration. So a variety of missions are possible using this engine. We've said how fourth generation engines comprise two cavities, and here we have two 950 megahertz cavities, waveguide inputs, and they're mounted on two 360-degree gimbals, which provide thrust control in X, Y, and Z directions. So they produce a very useful engine for a variety of missions. Now we have to get both microwave power and liquid hydrogen into these cavities, and they need to be transmitted through the rotatable joints at each gimbal assembly. This is a bit of an engineering challenge, designing these joints, and inevitably there is a small amount of leakage. So the whole thruster assembly itself is contained within a stainless steel spherical casing. We use a scavenge pump to bring down the pressure inside this spherical casing to close to vacuum, and this pump is used to maintain vacuum continuously in spite of the small amount of leakage at the joints. It's a fairly lengthy process to bring down these cavities to 20 degrees K so that we can get superconducting operation of the cavity walls and achieve maximum thrust. So the cool down sequence actually involves, first of all, using liquid nitrogen, and then finally liquid hydrogen. So once we've brought the thruster assemblies down to this temperature, they are effectively kept at this temperature throughout their service period, and we use an auxiliary liquid hydrogen tank associated with each engine for this purpose. It also enables engine change to be quickly carried out during routine operations of these vehicles, and therefore enables basically aircraft type practices to be used during the sequencing of various missions for a single vehicle. The cavity design for this particular engine is a 950 megahertz resonant cavity operating in TE211 mode with circular polarization. It results in quite a short but large diameter cavity. D1, large end plate diameter, is 500 millimeters. D2, the small end plate diameter, is 306 millimeters, and the internal axial length is 261.9 millimeters. From this particular design, we would look for a QU at 20 degrees Kelvin of 7.98 times 10 to the 8th. That's a pretty huge Q. and with a design factor of 0.7511, we get a specific thrust of 4 kilonewtons per kilowatt. That's getting on for half a ton per kilowatt, which is a very useful specific thrust to get. And if you run this particular large cavity at its maximum power of about 80 kilowatts, that's 80 kilowatts microwave input, you'll get a maximum thrust of 320 kilonewtons. Yeah, so that's 30 tons, which is a very useful thrust for the sort of vehicles that we are going to look at and the sort of missions that we're going to analyze. The characteristics for this particular cavity are shown to the right. And you can see classic guide wavelength and wave impedance characteristics. The E and H field diagram to the left of the slide clearly shows the single half wavelength operation of this particular cavity. And you'll remember that we use this single half wavelength operation basically to reduce the Doppler shift under acceleration. The first and simplest vehicle that we will be looking at is our deep space probe. This essentially uses just a single fourth generation, and if you look at the diagram on the left, you can see that the bulk of its 13.4 meter length is taken up by the fuel tanks. Liquid hydrogen is the largest tank, with a small liquid oxygen tank at the top of the hydrogen tank. Now, the configuration is that the thruster itself, the thrust vector, is mounted above the center of mass during launch. And this is quite important because it enables a very straightforward launch to be carried out. Typically, if it's a ground launch, you can launch it directly from a tube mounted on the back of a truck. And in this launch configuration, once it's pointed vertically up, once the launch tube is raised to the vertical position, the probe itself is effectively hanging from the thermal interface at the end of the launch tube. Above this thermal interface, outside the launch tube, you can still have access to the payload during the last period of launch preparation, which can be quite useful. Below the thermal interface, everything is at cryogenic temperatures. Above the thermal interface, we have the SSPA fuel cell and the payload. So the launch tube itself would be a double-walled vacuum tube to minimize boil-off, and essentially the launch itself is absolutely straightforward. You simply switch on the thruster, the thrust will build up, and the vehicle itself will simply lift gently out of the launch tube under control of the thruster itself, because it's mounted in two-axis gimbals. So you've got pitch and yaw control from the thruster, the roll control would be carried out by a momentum wheel, as is classic in these typical missile type configurations. The mass budget shows that we actually get a total launch mass of 5.4 tons for a half-ton 500 kilogram payload. Very useful vehicle for all sorts of missions. Essentially, its primary design is for science missions into deep space. For our first mission analysis, we will use a very simple example of the deep space probe under space launch. So we'll make it as simple as we can for this first analysis. And you can do the analysis using a spreadsheet, and the columns of this spreadsheet are shown in the table, and the inputs are, if you like, in column A, which is a time increment, and the acceleration in column B. So essentially you carry out the mission analysis by line, varying the time increment for whatever particular mission phase you are in, and obviously you sum everything at the last line of the spreadsheet. So from the inputs of time increment and acceleration, you can calculate the various mission parameters using essentially standard equations from straightforward mechanics. So, for instance, column C, you calculate the terminal velocity at the end of each time increment. You need to calculate the velocity increment D and the average velocity over that increment. And then you can get the total distance in column F. And as I say, these are all standard equations that any physicist will be, or mechanical engineer, or even any engineer will be very familiar with. To calculate the fuel mass that you're using at each stage of the mission, you need to effectively know the microwave energy that you have used during that time increment. This enables you to calculate the amount of liquid hydrogen you've used to keep the thruster itself cool at 20 degrees Kelvin. You keep it cool by effectively evaporating the liquid hydrogen to keep it at this temperature, and therefore you can calculate the mass of liquid hydrogen that you use for each increment by using the latent heat of evaporation of liquid hydrogen, which is given in kilojoules per kilogram. So simply you calculate the mass used because you know the microwave energy you've used during that increment in kilojoules, and therefore you can calculate the liquid hydrogen mass in kilograms. To calculate the liquid oxygen you use, you need to know the DC energy you've used during that particular time increment. So you'll need to take into account the efficiency of the solid state power amplifier, and you need to know the liquid oxygen flow for the particular fuel cell that you're using. So this is a specified parameter for the fuel cell in kilograms per kilowatt hour. The clearly enables you to calculate the total fuel used in each increment, and you can integrate that as you work through the analysis line by line until you can end up with a zero fuel margin. In effect, if you're going to have no margin left at the end of the flight, then you'll simply just integrate until you've used up the total fuel, which of course then gives you a total propulsion period. So it's all a pretty straightforward technique using and is straightforward for anybody who's familiar with using Excel spreadsheets, which I'm sure we all are. So now we will look at the results for a mission analysis that we described in the previous slide. That is an in-space launch of our deep space probe. And the key results that you get from your analysis are shown in the two plots here. And in the left-hand plot, you can see that we've got distance travelled and velocity against the time that the thruster is being fired up. And what we've assumed for this particular mission analysis is that we have a nominal payload mass of 500 kilograms, and that we continuously fire the thruster at its maximum thrust, which you can do if you're launching in space. The analysis gives us a terminal velocity of 863 kilometers per second. Yeah, this is pretty fast. And this is achieved after a total thrust period of 185 minutes. Now, the distance you cover during this thrust period is 4.3 million kilometers. So you do this in the first 3 hours of flight. So you can see why this is indeed a deep space probe. It's quite a useful vehicle for scientific investigations into deep space. If we look at the acceleration that we're going to get during this thrust period, you can see that even at the start with the maximum fuel load, you're accelerating at 6.1 g, and the final acceleration is as high as 11.3 g. So these are continuous acceleration levels that are perhaps more typical of a missile than a standard spacecraft. So the structural design of both the probe and the payload itself must take these acceleration levels into account. The second characteristic which we see in the slide at the right hand side is a plot showing the fuel margin as it's used up during the thrust period. This is particularly useful because it means you can start to trade off your fuel margin for additional payload mass. So depending really on what your mission targets are, you can carry a much heavier payload, but you won't go quite as far and quite as fast during the thrust period. If you look at this particular plot, you can see that if you want to have an additional 1,000 kilogram payload, this will reduce the thrust period to 110 minutes, and the terminal velocity will be reduced to 450 kilometers per second. So it's a useful characteristic to have, it's the fuel margin. The next vehicle design we'll look at is our heavy launch vehicle. Now, this is a design that has developed over many years from an initial suggestion by the US Air Force. They described their requirement actually as they needed a space elevator without the cables. And this indeed is what the heavy launch vehicle is designed to provide. It's primarily to launch large, heavy payloads to geostationary orbit. You can see the design outline on the left. And in the plan view, you see how the 8 engines are configured. Each thruster is associated with an auxiliary liquid hydrogen tank. It has its own SSPA and fuel cell. And these actually can be interconnected for redundancy purposes. The design is pretty straightforward. You have the 8 thrusters arranged in the main thrust frame, above which you carry a very large triangular liquid hydrogen tank, and below which you hang the payload. Now, the idea is that the mission itself should be designed so that you accelerate quite slowly through the atmosphere. So you don't have aerodynamic problems, and indeed the payload can be carried unfaired, which is quite useful for once you get to geostationary orbit, because you can in fact deploy the payload quite easily. And essentially with the 8 thrusters, all of which are fully gimbaled, you get tremendous maneuvering ability once you're on orbit. And of course you get complete flight control during vertical takeoff and landing and during the acceleration period. The vehicle was originally specified to be fully reusable and specified for a minimum lifetime of 500 missions. This, as you'll see later, gives a very low-cost launch to geostationary orbit. And for a geo mission, we can carry 65 tons of payload, and you'll see that from the mass budget given in the slide, you'll get a total launch mass of 116.8 tons. We'll now look at a mission analysis for a ground launch to orbit. And this is rather more complicated than the simple space launch mission that we looked at previously. And clearly we're going to need some additional columns in our spreadsheet calculation. The first thing we have to take into account is atmospheric drag during the period that you're actually in the atmosphere, just after launch, and we calculate that from the equation shown in the slide, where we need to know the drag coefficient of the design, the vehicle design. We need to know the air density at the altitude we're at, frontal area, and the vehicle velocity. Now, for simplicity, what we've done is divided the air density value into 8 ranges of altitude, and you can see that above 100 kilometers we've assumed that the air density is so low that can be negligible. We need to calculate the Earth's gravitational acceleration to the particular height that we're at, and you can see that's calculated from the equation given. It gives a value of g in meters per second squared. And we also need to calculate the balance against the Earth's gravitational force, which is the centrifugal force that we get to any horizontal component of the vehicle's velocity. And this, of course, is why you obtain orbital conditions when the centrifugal force that you're generating from the horizontal velocity balances out the Earth's gravitational acceleration. So you can calculate the centrifugal force from the equation given, which is yet another column in the spreadsheet. The idea is you aim to calculate the total thrust requirement from both the lift force required to overcome gravity, less the centrifugal force, and also the thrust required to accelerate the vehicle in both the horizontal and vertical directions and to overcome atmospheric drag. So it becomes a rather more complex spreadsheet. Here we look at the mission analysis results for a heavy launch vehicle launch to geostationary orbit. And on the left, we can see a plot of altitude, rate of climb, and velocity against flight time, which is a total of 92 minutes. So this is a long, slow climb to orbit. And you can see initially, if we look at the rate of climb plot, which is the red plot in this characteristic, that the initial rate of climb is very low, and you do this by throttling the thrusters right back to limit the atmospheric drag. If you look at the acceleration profile on the right-hand plot, you can see this very low acceleration level initially as the thrusters are throttled back. Essentially, this is so that we limit the velocity through the atmosphere and therefore limit drag and limit aerodynamic effects on the payload itself, which, remember, is being hung unfared below this horizontal attitude of the thruster of the vehicle as it accelerates upwards. Now, once you're clear of the atmosphere, the vertical climb reaches a maximum of 11 kilometers per second. And we actually have a maximum vertical acceleration, which you can see on the right-hand graph, of about 1.3 g. So this is a gentle launch profile and therefore reduces stresses on whatever payload it is that you're carrying. You achieve orbital velocity by 32 minutes flight time, but the climb continues under the deceleration of reducing gravitational force and, of course, the effect of centrifugal acceleration that is given by the orbital velocity. Now, at 82 minutes flight time, the thrusters are actually rotated through 180 degrees to produce deceleration for a period of 10 minutes, so that the climb rate itself reduces zero by the time you reach the geostationary orbital altitude of 36,000 kilometers. So now we'll look at a completely different vehicle, a manned vehicle, which we've termed a personal spaceplane. And this itself is one of a family of these 4-engine vehicles, each of which uses 4 of what's now become the standard fourth generation engine that we're talking about. Now, the family of vehicles range from a three crew Mars transfer vehicle through passenger or freight suborbital transport and short haul air taxi applications. But the original design requirement was to transport a crew of 6 to the moon, to carry out a vertical landing on the moon, followed by a short stay and a safe return to Earth. And the primary market for this vehicle was seen to be space tourism. Now, because we're carrying a crew, we need a passive docking hatch, which would enable in-space transfer of crew in any emergency, and also would enable access to a moon base once you've landed on the moon. If you look at the configuration of the engine mounting given in the diagram on the lower left-hand part of the slide, you'll see that the basic thruster casing itself is mounted on an L-shaped plate to give thrust transfer in horizontal and vertical axes. The fuel cells and SSPAs are mounted alongside the thruster, and in the case of this manned vehicle, they are completely cross-coupled to give good redundancy, such that the idea is that in a single engine emergency capability, you'll get landing, an emergency landing, using the auxiliary hydrogen thrust, the auxiliary liquid hydrogen tank, which is mounted alongside the engine itself. So there's this also, of course, gives you, as we mentioned before, a much easier servicing routine when you can just swap out engines whilst keeping them at their 20 degrees K temperature. So we'll now look at the personal spaceplane in its moon mission configuration. And if you look at the diagrams to the left of the slide, you can see that in this case we have the crew cabin mounted above the thrust frame containing the 4 engines, in a similar configuration to the heavy launch vehicle that we saw, but just with 4 engines. The main fuel tanks, the liquid hydrogen tanks, are actually below the thrust frame and to the front of the vehicle itself. Now, the cabin, the crew cabin, is quite large. It has full life support facilities, which includes spacesuit storage, and the seats are fold down so that during the cruise period of the mission, the passengers can enjoy zero-G experiences. Part of the marketing for space tourism applications. It has a rear-facing docking port, and the high maneuverability of the 4 engines allows straightforward docking in space if you, for any reason, needed to carry out an in-space rescue of the passengers and crew. Again, from a safety consideration, the vehicle airframe design is such that you can have an emergency glide landing where you would use upper and lower elevons to give pitch, roll and yaw control, plus air brakes to slow yourself up for a horizontal emergency landing. In this particular case, you would use a fast helium purge system, basically to empty the liquid hydrogen tanks, and this will improve the overall crashworthiness of the vehicle itself. Safety considerations, particularly for space tourism applications, are very important. And you can see that the interconnection of the 4 engines via the fuel cells and SSPAs gives a very high level of redundancy, and the 80 kilowatt rating of a single engine allows emergency single engine landing if necessary. You wouldn't actually land in a very optimal attitude, but nevertheless you would get down and land using only single engine operation in this very dire emergency situation. You can see that from the mass budget we give in the table there, assuming a 5-ton payload, the total launch mass for a moon mission is 21 tons. We'll now look at the mission analysis results for the moon mission. This is for the forward flight from Earth to Moon. And if you look at the left-hand plot, you'll see we're plotting the acceleration of the vehicle in red. And importantly, this is the vehicle acceleration in the from a passenger's point of view, actually, because it's the forward acceleration that the vehicle is seeing. And therefore, with the passengers in their seats, it's also the acceleration that they are feeling. We also plot the Earth's acceleration, gravitational acceleration, which is shown as green dots, and the moon gravitational acceleration, which is shown as the dashed blue line. The vehicle acceleration is shown as the red line. And we see in the second plot the vehicle velocity, which is shown in red. Both horizontal axes are the mission time in minutes. And you can see that initially with a vertical takeoff, with the vehicle in a horizontal attitude, the acceleration is initially very low, around 1 meters per second squared, until we get to an altitude of 100 kilometers. Now this again is to minimize air drag, and we actually get a maximum drag force of 2,161 kilograms occurring at an altitude of 10 kilometers and a velocity of 100 meters per second. Now, once clear of the atmosphere, the acceleration, as seen from the profile, increases to 9.81 meters per second squared, which is 1 G, so it's quite comfortable for the passengers. And this carries on for almost 60 minutes until you get to a distance from the Earth of about 150,000 kilometers. Now, at this point, Earth's gravity is close to zero, as you can see from the green dotted line in the left-hand characteristic, and we shut down the thrusters, and we have a 96-minute cruise phase at 0 G. Now, at the end of the cruise phase, we rotate the vehicle 180 degrees, which allows a 1G deceleration phase to start. And this can be carried out without any passenger disorientation, because they're merely being pushed back into their seats at the 1G level that they've been used to on Earth. Now we have an initial 1G deceleration period, and once we get to 360,000 kilometers from the Earth, we reduce the deceleration down to 2.61 meters per second squared, and this brings us into the ability of a vertical landing at the correct place on the moon's surface. We have covered then a total flight distance of 384,415 kilometers, and it's taken a total flight time of 262 minutes, which is a 4-hour, 22-minute flight, which is, I would suggest, very acceptable for space tourism flights to the moon. So it's now your turn to start doing some work, and I'm going to suggest some exercises that you can carry out using your own mission analysis software based on the Excel spreadsheets that you will have undoubtedly produced by now. So if we look at what we can learn from these mission analyses, first of all, and let's look at the moon mission analysis. And one of the interesting things is how can we make these moon flights as safe as we can? And one of the parameters we need to look at for this is the fuel margin. If you do a fuel usage plot for the outward mission, you can see it shown on the blue line in the plot shown, and you'll see that you will actually use a total of 1,309 kilograms of fuel for the outward flight. If you look at the mass budget shown below for fuel for the personal space plane, you can see you have a total fuel capacity of 2,818 kilograms. So if you assume that the same fuel is used for the return flight, the total fuel margin you're left at the end is only 8.5%. This might seem a bit low for a tourist flight to the moon, so it would be interesting for you to look at how you can improve this fuel margin, in spite of the fact that if you did run out of fuel, we could fairly easily launch a space rescue mission. But nevertheless, it's a good and very practical view to take as to how you can increase fuel margins, indeed, for any mission that you're carrying out, certainly any manned mission that you're carrying out. A second mission analysis which I recommend you do is for a ground-launched deep space probe. So here you now have to take into account the drag, atmospheric drag, as you go through the initial launch. You need to see how much you have to throttle back the engine and to achieve a satisfactory flight profile. Another mission that would be worth doing is to do an analysis of global suborbital cargo deliveries, particularly for the heavy launch vehicle. In other words, how can you transfer 65 tons from one place on the Earth to another place, perhaps up to a full global range. So you want to fly this payload halfway around the world. I suggest what would be fascinating would be to carry out suborbital passenger and cargo delivery missions using the personal spaceplane, for instance, from London to Seoul. What would be the trade-offs between payload and fuel margin? What altitude would you fly at? What speeds would you achieve and acceleration levels? All of these are variables that you can try out in your analysis software, which you've now developed, I'm sure. Finally, it is worth looking at the system efficiencies for these various vehicles and missions, particularly, for instance, for the Deep Space Probe. This system efficiency gives a very good overall view of the mission and is a good parameter to use for comparing between the results of different missions and different vehicles.